So the problem this lab report is covering is how the energy principle is satisfied with a mass spring system. The result I found is that all the components of energy within and outside my mass spring system do in fact satisfy the energy principle. This is the video given to us in class to analyze. It shows a mass on the end of a spring held down and then released. The motion was tracked and then replicated using VPython. Now, how I replicated this with VPython was to first set the initial conditions, force of gravity, mass of the ball, length of the spring constant, etc. And then I updated it by at each point calculating the force of the spring, calculating the force of gravity, and then adding them up to get Fnet. Using Fnet, I could use the momentum principle to update the position of the mass on the end of the spring at each point. So when I run this code, here you're going to see the mass following a certain path on the end of the spring. And when we compare that to this graph in Excel, which I made based on the observed data in the video, you can see that it follows the same path. They both follow kind of a weird elliptical path that makes a square border around the outside. And I also had the VPython program predict the end position of the mass, which is not exactly the same end position as it is in the video, but it's very close. It's 0.0999, which in reality was like 0.095-ish, and then for the y component it was negative 0.64 in my prediction, and in actuality it was negative 0.664. So they're very close, which is about all you can ask for, since tracking the position of the mass in the video is not that exact. So they do end up in a very similar position. So now for the what does it mean part of the lab. The first part asks us to compare the x and y component periods of oscillation to each other. So when I run the code, this graph here is comparing those two oscillations to each other. The y-coordinate is the bottom sinusoidal curve, and the x-component is the top sinusoidal curve. The x period is slightly larger than the y period because the original stretch of the spring was more in the x direction than in the y direction, meaning it takes longer to travel in the x direction. For the other question, with a new choice of system, making the spring now part of your system, which means it gets calculated as potential energy instead of work done on the system, you can see, here's a graph, here's potential gravity, potential spring, kinetic is green, and the total change in energy is the red line here, which is constantly at 0, which makes sense because the total energy of the system shouldn't be changing since no work is done on it. And no work is done on it because everything that's affecting the system is within the system. There's the mass, the spring, and the earth all in the system, and there's nothing else on the outside to do work on it. And for the last question, changing the origin and how that would affect the physics of the system, ultimately it doesn't affect the changes in energy because no matter where it is, as long as the mass is still close to Earth, so that 9.81 is a good measure for gravitational force, the changes in energy are all going to be the same. So they're still going to come out to a total of 0, and they should be relatively similar. Now, however, the only way it would change is if you moved the mass so far away from the Earth that the gravitational factor did change, in which case your potential gravity down here would be different, but overall your total change in energy would still be a line at 0, since the energy is still not changing.